Hello everyone, in this video we are going to look at the basic ideas behind the common machine learning models that are used for both regression and classification problems. Specifically, we look at a support vector machine, a decision tree, a k-nearest neighbor, a random forest, a gradient boosting machine, and also its variants. So let's start from that of a support vector machine. But before that, let's consider how the logistic regression model is used for a classification problem. In the usual generalized linear models, we have a linear predictor, which consists of the linear combination of the covariates, which can be written in this form. So this is the decision boundary for a logistic regression model. And in short, if this linear predictor or linear combination of the covariates is greater than or equal to 0, that means it is predicting, let's say, class 1, but if it is less than 0, it is predicting, let's say, that's of class 2. And specific to logistic regression, this linear predictor, which may assume any value, positive, negative, or 0, should pass through a sigmoid function. Then this sigmoid function will convert the linear predictor into a value between 0 and 1 inclusive. So this decision boundary could be, for example, the line represented by A, or it could be the line represented by B, or it could be the line represented by C. Therefore, we could have, let's say, particularly specific to these plots, we could have 3 different logistic regression classification models. Now, if we look at the performance of these 3 models, they all make a prediction accurately, or the performance of all the 3 models for this particular training data set is 100%. That means they accurately classify both the blue and red dots, assuming a binary classification model. The color red representing one class, let's say, and the color blue representing another class. However, here the decision boundary for A is close to the red points, and the decision boundary for B is close to the blue points, and the decision boundary for C is close to both the red and the blue points. Therefore, for example, if we have, let's consider decision boundary C. Then here, for example, if we have a certain point somewhere around here, let's say, based on the decision boundary of C, this point could be classified as red, but this point is more close to the blue points. Similarly, if we consider the decision boundary for A, and if we have a certain point somewhere like here, let's say, then this point could be classified as blue, but in fact this point is more close to the red points. So even if the performance of these 3 models or these 3 decision boundaries is 100% accurate, just we could have another way of just maximizing the margin. So for that, we need to consider what we call a support vector machine, which minimizes half of that of the squared norm of the weights subject to the constraint yi times the linear predictor greater or equals to 1. So the idea here is, in general, we will consider one hyperplane for that of, let's say, the blue points, and we could consider another hyperplane for that of the red points. Then the objective is to maximize the margin or the distance between these 2 hyperplanes. So in the support vector machine, just the decision boundary could be the one that is represented by a broken line. So this broken line is far from the blue points, and at the same time it is far from that of the red points. So the objective is to maximize this margin or the difference between the hyperplanes of the different classes. And another thing, in the logistic regression model, we could have n observations. All the n observations contribute in estimating the parameters of the decision boundary or the parameters of the logistic regression model. But when it comes to that of a support vector machine, it depends on a few points which are specifically called support vectors. So for example, the decision boundary here, the broken line, depends on 3 points. This point 1, this point 2, and this point 3. But all the other points will have no contribution in estimating the decision boundary. So in general, a support vector machine is a supervised learning algorithm that is used for both classification and regression problems, but most of the time a support vector machine is applied to binary classification problems. So support vector machine finds the best separating hyperplane, or that is the decision boundary that maximizes the margin. So margin is nothing but the distance from a hyperplane to the nearest points from each class. And particularly those nearest points from each class are called support vectors. And these points determine that of the decision boundary of the support vector machine. So all the other points that are different from the support vector machine will have no contribution in estimating that of the decision boundary of the model. And here specifically we have considered a linear logistic regression model and that of a linear support vector machine, and actually a support vector machine can handle also nonlinear classifications or classification problems that cannot be separated by a straight line. But this support vector machine has the possibility of handling nonlinear classification using what we call kernel functions without the need of transforming the original data. So compared to that of the logistic regression model, the support vector machine has some advantages. One, it can work well in high dimensional spaces, and the other, it can even be applied when the number of variables or the number of dimensions are larger than the number of samples or examples or observations. But if the number of variables are greater than that of the number of observations, most of the statistical models cannot handle the problem. But since support vector machine depends on a few points which are called support vectors, it can be applied even if the number of dimensions or the number of variables are greater than that of the number of samples or the number of observations. And another, it is also robust to outliers because it depends on only on a few points which are called again support vector machine. Support vector. Support vectors. And now let's look at that of a decision tree. Now a decision tree splits the data by asking a series of binary questions that can be answered something like yes or no. And the objective is to create a flow-like structure by recursively dividing into smaller subsets. And at each split, the objective is to maximize the information gain or to decrease the entropy. And it's usually interpretable, but as long as the depth is larger, decision tree could have the problem of what we call overfitting. So the depth should be determined appropriately. So the idea is, for example, if we have two variables, let's say, which says the time of the day and which says whether the individual is tired or not. So it starts by splitting the data, something like what is the time of the day. If morning, then it asks another binary question, are you tired? Then based on the answer, whether it is yes or no, we need to determine number of individuals belonging to the different classes, let's say for a classification problem. Similarly, what's the time of the day? If it is afternoon, then next we have to ask, are you tired? Then the response could be yes or no, and then we have to determine the number of outcomes under each response. Therefore, the way that a decision tree works is just in this form, by splitting the data through asking a series of binary questions and recursively dividing the data into a smaller subsets with the objective of maximizing the information gain, or with the objective of decreasing the entropy at each split. So for example, let's consider this example. Here we have, let's say, 14 samples or examples, and we have particularly 5 variables: age, sex, blood pressure, cholesterol, and drug. Let the drug variable be our outcome variable of interest, and let's consider all the other 4 variables as covariates. So from this data we can easily construct this decision tree. Then for example, first we have age, and then we need to identify the categories of age, let's say. Then the individual may be in the age of 18 up to 13, otherwise in 36 up to 50, or in greater than 50. Once we know the age, next we have to ask the next question: the sex of the individual, it could be female or male. And finally we have to identify our outcome variable. And the same is true here. If the age is between 36 up to 50, then we can ask for age, and we can ask for other variables, and finally the outcome will be B. And for the age greater than 50, we can ask for cholesterol, and then whether the cholesterol is high or normal, we can determine the outcomes. So here, for example, we have 4 variables: age, sex, blood pressure, and cholesterol level. In constructing this decision tree, we can see that blood pressure has no impact in predicting these outcomes or in predicting the drug. Therefore, one of the advantages of this decision tree is it can be used as a feature selection method. So of these 4 variables, blood pressure has no contribution in predicting the drug. And second, for example, you can see that once the age of the individual is in between 36 up to 50, we can easily see that it automatically predicts the drug type as B, regardless of all the other factors or factors like sex, cholesterol, and the other variable, let's say blood pressure. So decision tree has just the importance of identifying important variables or variables having the greatest contribution. But here just I considered this example to illustrate how a decision tree can be constructed. Otherwise, for this particular data having only these 14 observations, this decision tree could be an overfitting decision tree. So consider this just as a method of illustrating how the decision tree works. So for example, if I have given the age, sex, blood pressure, and cholesterol level, we can predict the drug types. So if the age is 50, greater than or equals to 50, or specifically that's greater than 50, let's say, and if the sex is male, here sex has no impact, blood pressure has no impact, cholesterol normal, then the predicted value would be B, or the predicted drug type will be B. For the second, for the age 36 up to 50, regardless of all the other characteristics, the predicted drug type is again B. And for the age 18 up to 35, and if the sex is female, and regardless of cholesterol level, the predicted drug type would be A. So this is the idea how a decision tree works and makes prediction. Now let's consider the k-nearest neighbors machine learning algorithm. Now in the k-nearest neighbors machine learning algorithm, we are going to consider the k closest points to a particular value, say x, using Euclidean or other distance measure. Then we are going to make predictions for a new data point x. So for a classification problem, majority class votes is going to be considered, and for a regression problem, averaging the values of the neighbors is going to be considered. And specific to k-nearest neighbors, there is no training phase. All the computations happen during inference or during prediction. So this method is actually intuitive and it is easy to implement. But the disadvantages, it can be slow when we have a data set having a large number of observations, because we are considering only the k closest points. So here, for example, let's consider, suppose we have a classification problem. One denoted by that of the yellow points and the other class denoted by that of the purple points. And let's consider the three closest points, or let's consider where k equals 3. Then if we consider k is equal to 3, and suppose we are interested in predicting a point here for that of the red point, let's consider we are interested in predicting a value here. Then considering the 3 nearest points, since it is a classification problem, majority vote will be considered. So this red point would belong to that of the purple class. Now if we consider 6 neighbors, in that case, this red point would belong to that of the yellow class. But for that of a regression problem, we are going to consider averaging the values of the neighbors. So for k is equals to 3, if it is a regression problem, there will be no difference in colors among these points. So this predicted point will be the average of this point, and this point. Similarly, for k is equals to 6, we can consider the average value of all these 1, 2, 3, 4, 5, 6 points. So this point would belong to or the predicted value for this point would be the average value of the 6 points. And now let's consider that of a random forest. Now a random forest is an ensemble method which consists of different decision trees, and it uses bootstrapped samples or observations and random subset of features at each node. And then the predictions are going to be combined by majority voting for classification problem and by averaging for regression problems. So this random forest is nothing but it is an ensemble method consisting of several decision trees. Then here, for example, let's consider this random forests problem. Here we have decision tree 1, decision tree 2, and decision tree 3. Then the number of features and the number of observations in each decision tree may be different because it uses bootstrap samples or observations and random subset of features at each node. Then for decision tree 1, we will make a prediction, let's say result 1, and for decision tree 2, we will make a prediction, let's say result 2, and for decision tree 3, we will make another prediction, let's say result 3. Then if the problem is a classification problem, majority voting will be applied to make the final prediction, but if it is a regression problem, averaging the results will be considered. So for example, let's consider, suppose we have a fruit classification problem, and suppose we have a random forest algorithm based on 3 decision trees. So for example, the first decision tree could predict, let's say tree 1, the second I mean, the first decision tree could predict that of, let's say, an apple, and the second decision tree could predict, let's say, again an apple, and the third decision tree could predict, let's say, that of a banana. Then it is just a classification problem. Therefore, by majority voting, the final prediction would be an apple. The final prediction would be an apple. So this is the idea behind the of a random forest. And now let's consider gradient boosting machine. Like that of random forest, again gradient boosting machine is also an ensemble method consisting of several, let's say, learners or decision trees or any other algorithms. So typically just the number of decision trees to be considered are assumed to be shallow, but it is an ensemble method, then it is assumed to be the joint performance of all the shallow decision trees or all the shallow algorithms will provide an accurate estimation, or it will have an accurate performance. So unlike that of the random forest, here in the gradient boosting machine, the trees are building in a sequential format, and at each new tree the residuals are going to be used for making prediction. And finally, we are going to consider what we call an algorithm gradient descent in order to minimize the loss or the training error. So for example, let's consider, suppose we have three decision trees. Decision tree 1, 2, 3. In fact, we could have just, let's say, early decision trees. Then the prediction made is in a sequential manner. Then for example, for the first decision tree, we will make a prediction based on the inputs and the outputs, and then we will obtain the residuals for that tree, and these residuals obtained for the first tree are used as an outcome variable for the second decision tree. So we fit the covariates on the residuals of the first decision tree, and next we will obtain the residuals for the second decision tree, and these residuals of the second decision tree are again used as an outcome variable for the third decision tree, and by fitting the covariates on these residuals, again we will obtain the residuals for the third decision tree, and just it continues until predictions are made for all decision trees. So the final prediction will be y hat, which equals y hat 1, this is the first prediction, plus lambda times residuals of the first decision tree, plus lambda times residuals of the second decision tree, plus lambda times residuals of the last decision tree. Here lambda is called a learning rate that's going to be applied in the gradient descent algorithm. So the idea here is, it is just gradient boosting is just an ensemble method, or it consists of several weak learners, or let's say ensembles, but in the random forest the trees are assumed to be parallel. We make a prediction using each tree, and finally the final prediction is determined by majority voting for a classification problem and by averaging for a regression problem. But for that of gradient boosting, the trees are assumed to be sequential. The trees are assumed to be sequential. So this gradient boosting machine is most powerful compared to the other methods in most of the applications. There are also other variants of this gradient boosting machine, which are called adaptive boosting, extreme gradient boosting, light gradient boosting, and categorical boosting. So the adaptive boosting or AdaBoost is actually not gradient based, but it is a variant due to its boosting nature. because it uses different weak learners, and the performance can be boosted just by combining or by making an ensemble of those weak learners. And in the case of extreme gradient boosting, it is an advanced and regularized version of that soft gradient boosting machine. The original gradient boosting may tend to an overfitting problem. So in such case, just this is a regularized version of the gradient boosting machine. So it can reduce overfitting, and it has also a means of treating missing values, and even it can apply what we call parallel processing in order to facilitate the speed of computation. And we have also a light gradient boosting machine, or light GBM, which is essentially optimized for speed and efficiency. So compared to the extreme gradient boosting, it is faster, but it may overfit more easily. And the other is a categorical boosting, or cat boost. It is specifically designed for handling categorical features automatically. So these are the most common machine learning techniques that are used for regression and classification problems. That is a support vector machine, a decision tree, k-nearest neighbors, random forest, and that's of gradient boosting machine and its variants.